Hello, good evening, everyone. Am I audible? Hello, am I audible, everyone? Hello, very good evening to everyone. Welcome to the second day of our FDP. Now, uh, today I would like to invite you to today's speaker. Uh, Let me introduce our today's speaker. But today's speaker is distinguished speaker, Dr. Devesh C. Jinwala, a professor in the Department of Computer Engineering at the Sardar Vallabhbhai National Institute of Technology, SVNIT Surat. Dr. Jinwala has been a faculty member at SVNIT since 1991, contributing significantly to the field of the information security, machine learning, and their application in the healthcare. He holds a PhD in computer engineering from SVNIT Surat, where he conducted his doctoral research in a close association with the Space Application Center and ISRO Ahmedabad. His research interests encompass information security and privacy, machine learning, and the development of robust AI system for resource-constrained environment. Dr. Jinwala has authored over 150 publications and has been actively involved in a various research projects, including those focusing on adversarial machine learning and its implication in the cybersecurity and healthcare. He has also served as an adjunct professor in computer science and engineering at IIT Jammu. Today, Dr. Jinwala will be deliver a talk on adversarial machine learning in the healthcare, exploring the vulnerability of the AI system in medical application and discussing the strategy to mitigate the adversarial attacks to ensure the safety and reliability of the healthcare technology. So it is my pleasure to hand over the session to the Dr. Devesh Jinwala, sir. Over to you, sir.
Yeah, good evening to all. Am I audible?
Yes, sir. Yes, sir. Good evening, sir.
Yeah, so thank you for that
Very welcome, sir, on
kind.
behalf of Government Polytechnic, sir.
Thank you very much. Thank you for that kind introduction also. And please give me some time so that I can share the presentation.
Okay, sir.
So is my screen visible? Hello, can somebody confirm whether my screen is visible or not?
Yes, sir, your screen is visible.
Okay, thank you very much. So, this talk is about an overview of adversarial machine learning in the healthcare. And I have shown it as 1 and 2 because in order to basically understand the concept of adversarial machine learning applied to any domain, first we have to get an understanding of what is adversarial machine learning. So what I would do is I'll try to talk about some basic concepts revolving around adversarial machine learning initially, then go into the you know actual attacks and the defense mechanisms which can be applied to healthcare domain. And the contents of the presentation would go around like this. So as I said, the first part is having basics of adversarial machine learning, which starts right from machine learning and the security concepts, how the attacks comes into the picture in machine learning, And what are the two paradigms followed in security in which this machine learning security can be looked into? Then definition of adversarial machine learning, and then modeling the adversary. In security domain, whenever we want to study security, uh, one of the most important functionality or component is to understand the capabilities of the adversary or capabilities of the attacker, which is known as adversarial modeling. So that is where we would be spending a significant amount of time, where in order to understand what are the attacks and what is the cause of the attack, we'll have to understand the capabilities of the adversary or what kind of attacks an adversary can carry out. So uh, one could say it is taxonomy of the adversarial attacks, and from then on we would go on to the second part where we are trying to specifically address the healthcare and the adversary generation. So attack generation strategies in healthcare. What is the attack surface in a typical healthcare application as compared to any other application? What are the adversarial defenses and the mechanisms for defenses or strategies in general? The taxonomy of adversarial defenses. I'll talk about some of the approaches used in research in order to defend against an adversarial attack, and these are applied to healthcare. And finally, we would summarize. So, starting with the basics of information security, I would expect every one of you to be aware about this diagram or the concepts therein, which says security would be talked about always in terms of three components, which is the you know security attributes which we want from a typical application, like what is shown here as access control or authentication or non-repudiation or confidentiality and so on. We would also want to talk about what are the weaknesses, vulnerabilities, or threats which occur on a typical system, which would prevent us from getting the attributes which are shown in these 8 security dimensions. And what are the attacks which generate because of the threats or the vulnerabilities. And the third component, which is not clearly visible in this diagram, is the mechanism by which we would be providing these attributes. So suppose I want confidentiality, then what would be the mechanism which I would use to achieve confidentiality? This is the fundamental on which any talk on security would rest on. And so I am showing these two diagrams, wherein in this refined diagram, what we get to see is that for every security attribute, what could be the mechanism used to achieve it? Like it is, for example, if I talk of ensuring confidentiality of data, which is shown by my highlighted cursor, then the mechanism is encryption, and I get the attribute confidentiality. That is how the diagram is to be interpreted, and it is to be used as a basic reference. Because when we talk of adversarial machine learning, we would be using these terms in our discussion. So the essential questions which revolve around the mechanisms is how are the security mechanisms designed and deployed conventionally? How do they fit in the entire security orchestration or automation and response framework? And are there any characteristics to determine how to design and deploy this security mechanisms?
Sir, sorry to interrupt, but screen is not visible, sir.
So earlier I think I was confirmed that screen is visible.
एक्चुअली सर आपका पहले दिखाई दे रहे थे लेकिन करंटली स्क्रीन इज नॉट विजिबल सर. Now, sir, visible. Sir, visible. एक मिनट हो.
Hello, am I audible now?
Audible, sir.
Are you able to see my
And screen is
slides
also
changing?
visible, sir.
No, I'm
Now,
changing the slides. Please confirm whether you are able to see the slides being changed or not.
yes, sir, visible. Slides also visible, sir.
Okay, fine. So let me go ahead. What I was saying was I had introduced earlier the basics of information security, and I had said that security should be studied in terms of what is shown in this diagram, where there are certain attributes shown in this column where my cursor is moving. And in order to get these attributes, the mechanisms are shown alongside. Like to ensure confidentiality, one should be able to use the mechanism encryption. The reason I am talking about this 8 security dimensions applied to each security perspective is we would be using this when we talk of modeling the adversary slightly later. Uh, uh, in the design of the security mechanisms, that means in order to get a particular attribute, what mechanism should I use? There are certain important concepts which should be aware about, and I'll highlight about the fourth concept shown here, that is a reactive and proactive approach, because it has something to do with machine learning. So typically we must have heard the terms like firewall or intrusion detection systems or antivirus. All of this basically are referred to as the reactive cybersecurity measures. What we mean by reactive is they would look at a particular attack which is taking place and then build a counter mechanism to defend against those attacks. So what is written here is defense and response to attacks that have already happened. Instead of a priori thinking about a particular attack and finding out the weaknesses that would lead to the attack, which happens in proactive cybersecurity measure, in the mechanisms which are currently being used, whatever security we use today, they are all based on a reactive approach. So react to a particular sort of attack which is happening. In order to have a proactive approach, what we would need is we would need security by design. So if we think of software development life cycle, in that software development life cycle, we would build in security right from the stage when the application's requirements have started being gathered, and we would build in whatever other security mechanisms which we want. So this would be based on a priori forecasting that a particular attack can take place on a particular system, and that capability can only come if we use machine learning in building the security mechanisms. So that's where the marriage of machine learning and security takes place, and adversarial machine learning comes afterwards, because currently what is being advocated in research is to build security mechanism one should use machine learning approach, because that would be the proactive approach which would then result, would anticipate and eliminate the weaknesses in the system while remaining prepared to defend against the new sort of attacks which can come up. And therefore we need to use security, we need to use machine learning when devising security mechanisms. And that is largely based on privacy preserving data mining approaches, which centers around investigating data patterns, looking at data, and then based on that, anticipating how a system could be attacked. So that's where, as I said, the artificial intelligence or machine learning, they come into picture, and they have revolutionized the proactive cyber security strategies. So they enable more accurate threat detection. They would allow early detection because now it is based on the investigation of data a priori. So they would allow early detection of emerging threats which were previously unknown. They would do so by analyzing vast data sets, which is what I have been emphasizing time and again. They would identify the weaknesses or the patterns which lead to weaknesses or the anomalies and potential threats in real time. And because AI excels in behavioral analytics, analyzing the behavior, they would be able to distinguish, using AI would be able to distinguish between what is normal behavior and what is the behavior which includes some attack. And that's how one would be able to strengthen the security system. So if you see today, the question as to where is ML used in cybersecurity application, then you would note that in research, typically for every kind of security attack which we have been thinking about, whether it is antivirus or intrusion detection and prevention, or it is malware detection and prevention, or defending against the network weaknesses, the web threats which are there taking place on the World Wide Web. In all these areas, the machine learning, either it is in the form of supervised or unsupervised learning or reinforcement learning or deep learning, one of these mechanisms, techniques are applied in order to devise the security solution. So that is what is shown, again summarized in this diagram, which says, as I said sometime back, protecting the weaknesses on the network, protecting the weaknesses or vulnerabilities in the endpoints, which means the computer systems or the nodes, protecting the application security. So I talked about the web attacks, SQL injection or malicious URL detection or phishing detection or spam detection. All of these form in application security. Or protecting against the anomalous user behavior like keystroke dynamics detection or breaking human interaction proofs using captchas or process anomalies. So everywhere in the applications or in network security, the machine learning is used. So this diagram is a kind of summary of the individual sort of machine learning based security mechanisms where all machine learning is applied on. And I'll not go into explaining each of them because our focus is somewhere else. Uh, so if you look at the workflow, machine learning workflow in a typical cybersecurity application, then you would note it is similar to the workflow of a typical machine learning application, where you would be gathering the real-time data. Then based on that data, I mean, after sanitization and processing of that data, you would use the data for model training. And then based on that model training, you would try to use that model now in order to detect the attacks which could take place. So we have attack detection model because we are using machine learning for cybersecurity applications. So if at all I am using machine learning for a conventional, say, classification application, then that classification here would be to classify between the data which could be the malicious data or one which is the normal data. So we are talking about, let's say, protecting against viruses. Then any incoming packet which can contain virus or which may not contain virus. This distinction now achieved using the machine learning model, and so we call it as machine learning workflow in typical cybersecurity application. So there are so many use cases for machine learning in security. Again, as I said, I would not go into listing out all of them. Some of them I already said before, like malware detection or intrusion detection and prevention, and so on. So this is only to sort of motivate you to understanding the importance of machine learning in security. So it's like marriage of different fields, marriage of analyzing data which comes from data science, uh, processing of the data which comes from data engineering, collection of data, and then refining that data, and cybersecurity. All of them basically using machine learning techniques to give us something which is an AI-based cybersecurity application. So the answer to the question, what can AI/ML do for cybersecurity application? We summarized earlier, cybersecurity or AI would be proactively trying to predict that this is how the system can be attacked, which is not happening in conventional security application, which is what we have to note. Okay, so that was about machine learning and security. So if you look at typical sort of curriculum which could specify this different areas of study, one would be able to say that first one would study a course on security, one would study a course on machine learning, then there would be a course on using machine learning for security, which is machine learning in security, and then would come the area where you would focus upon adversarial machine learning. So in briefly, if I try to summarize and say what is adversarial machine learning, I would state it like as follows. I would say that just as the cybersecurity designers use machine learning in order to build strong security mechanisms, I said some time back, proactively trying to defend against the attacks. So I'm using machine learning to protect my system. I'm trying to devise a security solution using machine learning. Just as the machine learning and cybersecurity engineers would use machine learning to build a mechanism, the attackers would not be silent. They are not fools who would keep watching the machine learning engineers and security engineers combine and devise security solutions. The attackers also would learn from that, and they would see how to disrupt this existing mechanism that is in the first place. But more importantly, they would learn how to use machine learning to attack a system, which is what is the last part of this entire thread of the topics which I mentioned. To recapitulate, what I mentioned was one would start with two parallel basics, information security and machine learning, go to understanding how machine learning can be used in security, and then comes the adversarial machine learning, where one sees how machine learning can be misused for disrupting the security. Okay, that is what one would call as the adversarial machine learning. So an overview of adversarial machining. That's what I would be talking about. And this is a typical machine learning development pipeline, which talks about a typical machine learning two different phases. Training phase. During training phase, we would have developed a machine learning model, and this model would be used with some validation data to do machine learning, a validation of the model which is developed, and then after ascertaining that the model works fine, it would be actually deployed. So what I have written here in the figure is typical ML development, training, and deployment stages, wherein after collecting some training data and analyzing such data via an ML algorithm, an ML model is obtained, and this ML model must be tested via validation data. If the performance of such a model is good enough, then the model would be deployed. But the problem which comes in here, try to understand this diagram carefully. I'm not even talking about problem. I'm trying to focus upon how we are using this model in security. So let's say I'm trying to look at some data, and I want my model to distinguish between what is benign, that is what is acceptable out of the incoming network packets, which are valid network packets, and I want to distinguish them from malicious network packets. So I want classification done. I want a security solution developed using machine learning. So therefore, if you look at the model, it basically classifies between
Sir, may I
benign.
interrupt you? Sir?
Yes.
Sir, your PPT is not visible, sir.
Oh. Why is this problem coming time and again? The sharing is getting out of place. Please keep interrupting me immediately as soon as you're not able to see the PPT. I don't understand why is it happening.
Yes, now it's visible, sir. Your screen is
Yeah.
visible.
So
Sir.
I could see here when I come out of the presentation mode, I'm able to see that it has come out of the sharing mode, but I don't understand why is it happening because I don't use Teams as such. Normally I use Meet only. Anyway, but as I said, please interrupt me as soon as you're not able to see the PPT. So I'll go back and share.
Sir,
And sorry for this.
Sorry, it shows your Gmail screen, sir.
That's really funny. But just now you said it's showing my PPT.
No, sir. Just only it shows your Gmail screen, sir.
Now,
No, sir, not yet.
please confirm as soon as you are able to see that.
Okay, sir. Sure, sir.
Now it must be visible.
Yes, sir. It's visible, sir.
Okay. So I'm trying to say that a typical ML development pipeline wherein machine learning is used for uh, a security application wherein we want to distinguish between what are benign network packets and what are malicious network packets. We are able to see something like this, wherein the model is able to distinguish between benign and malicious packets. When it is trained, when it is verified using validation data, then also we have a clear distinction that this is benign, this is malicious. So this is how I would want this model to work. And very importantly, what is written here is the key statement which says trained model is assumed to be free from any kind of attack which takes place. So keep in mind, I'm trying to say that we are devising a security mechanism, but while devising that mechanism, we are going to use the machine learning model to detect the attacks. But my model itself, I would assume that it is free from adversarial attacks. And adversarial machine learning basically is to make this assumption wrong. So it says that what can happen is during normal regular ML operation, we would be able to classify a sample as malicious. So if at all I am given a malicious sample, my model has been developed in such a way that it would be able to classify an incoming sample as either benign or malicious and identify a malicious sample properly. In actual case, what would happen is the ML system itself would have been attacked by the adversary. So it would have either sort of made my model such that it is not able to detect a malicious sort of packet, or it would have injected some data during the deployment phase. While my model is actually deployed, the adversary would inject some data which has not been used during training. And so my model is not aware that this particular sample should be detected as a malicious packet. And therefore, what you are able to see here is that something which is malicious, a sample which is deliberately introduced by an adversary, which my model is unaware about, and that malicious packet has been detected, classified as a benign sample. So what it says basically is by inserting perturbations in the input data, the data for which the machine learning model is not trained, an adversary would sort of try to fool the ML model and induce an incorrect classification or prediction or whatever ML application is. So that is what I am trying to consolidate by trying to use different such figures which say that this is the traditional machine learning training phase wherein I have distinguished, I have made my predictive model aware that this is the data to be used for training and this considered as normal data. This data would be the malicious data. My model is aware about this data during normal case, but when adversarial phase takes place, adversary would be introducing some data which my model is not aware about. And so we would say adversarial machine learning is happening now. One of the basic reason for that is the answer to the question or raising the question that were the ML models which are used for security application, they were designed with adversary in view. And the answer to that question is actually no. Because the models were not designed by keeping adversary in mind, because the typical, if you look from machine learning angle, because the models have been developed by assuming some noise which is known as stochastic noise, which is not which is the random noise. It is not a sort of uh, deliberately induced perturbation, the term which we used in a previous slide. So adversary would try to do that. Adversary would use something. It would use data which is actually a noise, but which is perturbation. It's not random noise. And my machine learning model basically understood only the random noise. So that is either by doing poisoning of the data used during training, the two popular attacks which we would be talking about slightly later, which is part of adversarial machine learning. What are the ways in which adversary can be modeled? So one of them is uh, using wrong data during training. Let us assume that I am a powerful adversary. I have access to the site where the machine learning model is being developed. So if I have access to that site somehow, I could be internal adversary. I am one of the people involved in development of the model, but I have vested interest. So I would try to influence the model itself. And this is something which you have to keep in mind. Either I would target the training data itself, which is known as poisoning. It is known indeed as a poisoning attack. I would poison the machine learning model, or I would, try to, I am the outsider adversary. In security, typical security attacks are either internal adversary or outsider adversary. So outsider adversary is somebody who does not have access to the training data, doesn't have access to the model. What this adversary would do is he would use the perturbations which I talked about earlier, and would supply that data which would give the output which the adversary desires, that is a malicious sample being detected as a genuine one. So that is known as evasing, or it is known as exploratory kind of attacks. So these are the poisoning in adversarial machine learning is referred to as causative, because I am trying to cause the machine learning model to do something wrong even with the valid data which is being presented. While when I talk of exploratory or evasion, I am trying to evade the machine learning model from generate predicting or classifying the correct output. So the output cause in both the cases is the same. The output is that I would cause machine learning model to falter, not work as per how it has been programmed. That is what is the central part of the adversarial machine learning, and it could be used in any of the security application to make that security mechanism fail, or it could be used in a normal machine learning application to cause that machine learning application to fail. So therefore, in adversarial machine learning technologies, it is known as either decreasing. The goal is to either decrease the overall performance, or to target misclassification, or to have induce bad behavior, or insert backdoors and the trojans in the system. But this entire different behavior give rise to different taxonomies in adversarial machine learning attacks. We'll come to that taxonomy slightly later on. But if we try to answer the question, what is adversarial machine learning? By now, we must be able to answer that as it is the investigation, study of the machine learning vulnerabilities in adversarial environments, how machine learning application is susceptible. Uh, and that could be on any of the security solution, or it could be on the existing ML system and finding out weaknesses in the existing ML systems. Uh, both of them, both the first and the second bullet, basically are the attempts to fool the models by supplying deceptive input, and the goal is to cause malfunction in a machine learning model. So it is the research in adversarial machining is the research that studies the design of robust ML algorithm. If you look at robustness as a property in software engineering, robustness is a property which gives us the ability that even when the input which is given to a software application is not the one for which it is designed, then also the software application will not simply hang, will not misbehave, will give us a decent sort of message that the application is not designed for this input, So please try different input, something which we achieve by an exception handler in a simple program. That is what is robustness. So here we say that adversarial machine learning is the study of the designs of robust machine learning algorithms in adversarial environments. I am giving here different views of this adversarial machine learning. I'll not go into each of these views, because the basic aims of adversarial machine learning I've already discussed earlier, so I'll skip the slides. Okay, so I talked about taxonomy, which, in order to find out how a system could be attacked or what results as a result of an attack on the machine learning system, I must look at the modeling of the adversary, which is, understanding the taxonomy or classification of different machine learning attacks. Because this area has been studied quite a lot, I'll show that by means of some of the screenshots of various industries. There is a beautiful paper which I would be citing slightly later. You could see, if you have noted, almost all my slides have a pointer at the bottom of the figure, the source from where the figure has been taken. And as and when that figure comes, I'll cite that paper. I'll bring your attention to that paper. The title of the paper itself is very important, very interesting. It says Adversarial Machine Learning, the Industry Perspectives. So what it talks about, I am doing a bit of forward jumping here in order to sustain your interest. The paper basically talks about the efforts made by leading industry houses. The paper is actually written by a collection of practitioners at Google and Microsoft, if I remember correctly. And they have sort of tried analyzing what are the practices which these leading industry houses are adapting in order to have security solution built into, machine learning built into their security solutions. I beg your pardon. So therefore, the title is interesting. What are the industry perspectives? It is obviously in this 1.5 hour, I'll not be able to discuss the entire paper, but I think I would be able to give you the basic substance uh, of what is this paper containing, based on which you would be able to, it is interesting to study that paper because it gives a lot of research directions which can be followed further. So this is Microsoft's view of, because it talks about the taxonomy on Microsoft platform, it talks about what can happen if at all the features are perturbed. If the attacker wants to perturb the features, then what all are the probable targets which it can adapt? What would be the output which the adversary would be trying to achieve, by perturbing the features or by doing any of the other attacks? Whether the goal of the adversary is to target a particular user or a particular system or a particular process like training or testing or some other phase of the machine learning system, and what is the knowledge available to the attacker. So the point which you have to learn from this and subsequent diagrams which I would be showing, all of them titled as the attack taxonomy, is that there are lot many research papers, lot of researchers have tried studying the modeling part of the adversary, and they have tried giving different sort of taxonomy of different ways of looking at the adversarial attacks, each of them giving us some insight. When we study adversary, this is a very common real world phenomena in which if we want to know how a thief is going to attack our house, if we want to know how our house could be attacked, we should try to understand the capabilities of a thief, so that we would know these are the probable ways in which he can carry out the attack, and therefore we would be able to safeguard against those attacks. So that happens here also. The taxonomies which have been studied so widely, the basic aim is that one should be able to know what are the adversary capabilities. One should know how adversary would be able to attack. So we are going to look at those diagrams slightly later. But an important question which would come up, which I think I should address before I talk about the taxonomy, is why do we talk about this adversarial machine learning, or why is it that the attacker is able to carry out this attack on machine learning systems? The simple reason for that, I am showing here the oldest machine learning paper. If you look at on the right hand side, this is the snapshot of the first paper which came on machine learning. And if you look at the title of the paper, it is pattern recognition. So the basic theme which I am trying to focus upon here as the motivation for adversarial machine learning is that machine learning systems were not designed with adversary in mind. And this unfortunately is true about, forget about machine learning system, it is true about every application. Like, you think of a simple mobile ad hoc network protocol like AODV. When AODV was designed, it was not designed with security in focus. People just thought that this protocol cannot be attacked. And later on, they found out that the protocol has been designed such naively that there are fields which are susceptible to be attacked by the adversary. There are fields in the header of the protocol which are susceptible to be attacked by the adversary. So then security researchers realize and they try sort of publish different papers and try modifying the protocol. That applies to machine learning and adversarial machine learning only. So in my slides here and somewhere down the line, the basic theme which I am trying to convey is the applications of machine learning. They were the conventional applications centered around pattern recognition. Whatever application you think of, the basic theme is recognizing different patterns. Today that has changed. The applications of machine learning have been in ubiquitous environment. Many new applications are emerging, and therefore the attack surface is increasing. What do we mean by attack surface? I'll be showing the attack surface slightly later, and I'll not go into the slides because they talk about different machine learning application. They are trying to, the slides are basically an effort to convince one who would argue that why should adversarial machine learning be studied, or why should such attack even take place on machine learning, the adversaries attacks. That is because when the machine learning systems were designed at that time, people did not know that this is how they can be attacked. So and today, because the applications of machine learning have increased in the span, there is a wider attack surface on which the adversary would be able to carry out the attack. This also gives rise to what is referred to as machine learning and security research conundrum. What we mean by that is most of the machine learning solutions, they behave as black boxes. These days we often talk about explainable AI, that in order to understand how a machine learning or a deep learning model is working, we must be able to sort of convey what is happening behind the black box, because a machine learning solution is typically accepted as a black box. But that also makes it difficult for the users and the security designers and the practitioners to make sense of the model prediction. If I understand what is happening behind the scene, then I would be able to devise a protection mechanism. Otherwise, what will happen is, if that model's weakness is somehow noticed by the attacker, then attacker would try to misuse it. And therefore, it makes difficult for users to actually detect when a system has been influenced by a malicious actor. So that is what is known as conundrum or conflict. On one side, we want security solutions which are driven by machine learning. But when a security solution is driven by machine learning, try to mark my words carefully, I'm saying when a security solution is driven by machine learning, the security practitioner would say that I don't understand what is happening behind the scene. And that makes this entire field pretty difficult. That itself is the real reason why adversarial machine learning has come into such an importance. Why the paper like adversarial machine learning industry perspectives has come up. So could humans not be assured of robustness of machine learning system? That is the question which drives all of them. And this is the one which I am talking about. These are the snapshots from the sites of, if you look at the title, Google, Microsoft, IBM, Gartner. You look at, most of the leading industry houses or survey houses, they would have a link somewhere in their site which would say that security and machine learning, these two are required to be studied together. They would either call it adversarial machine learning or machine learning based security solutions and so on. Still, that paper has not come. I'll talk about that paper as we go on. So I think I've answered this question. Where do this security risk come from? I showed this diagram earlier and I explained that the noise which we are talking about, that noise is random noise. it comes as per the randomization theory by Shannon, the stochastic modeling by Shannon. But the noise which is used in a typical machine learning system is not the random noise. It comes as a stochastic noise. And I'm trying to address this question, the question as to what all we are going into now, a bit detailed, more detailed as compared to the abstract explanation which I gave earlier. So I'm trying to explain how an adversary would be able to influence a typical security solution. So what is shown here is a spam filter which comes from this site which is known as Spam Assassin. So if you look at this URL, Spam Assassin is considered to be a very successful spam filter, available globally. What would this spam filter do? The machine learning model would have been built with certain features that, if at all the data, any machine learning system is data driven, that I think all of us know. So it would be trained using certain data features that, if at all the input has some characteristics like buy or Viagra or a sale advertisement, then attach some weights to this features. So in this case, buy is given weight of 1.0, Viagra is given weight 5, and what that classifier would do is it will compute the total score of this feature vectors. And it would have, during training phase, it would have been taught that the threshold for considering an incoming mail as a spam mail is if at all this feature score goes above a particular threshold. So here the threshold shown, for example, is 5. And because Viagra contributes 5 to alone to the total feature weight, the total score comes out to be 6. And so we would say that this incoming mail is a kind of spam mail. That is how a classifier would be able to work. And this classifier basically is a linear classifier. I believe you understand the meaning of the term linear. Either the classification is based on some naive data patterns, either a line or a plane, something like that. So I'm calling this classification which is based on simple pattern, because that pattern here is shown as we identify certain words in data patterns on in email spams, incoming emails, and we would say that, okay, if at all the summation of these weights is more than some value, consider that as a spam, otherwise it's not a spam. So you could see this example. The incoming mail consists of spam@example.it, and it consists of the words buy Viagra. Then the feature weights, as I showed earlier, were 6, and therefore it would be categorized as a spam mail, what is shown by red here. The classifiers weights were learned from training data. So this would have happened during training, wherein we would have known that the machine learning designer would have known that this must be the weight values to be attached in order to consider a mail as the spam mail. And that happens using, if we think of a neural network, then we know the perceptron would be used and error backpropagation would be used in order to train the model so that it is able to do this classification. But the question which comes up is, can such a linear classifier be used in spam filter? So why should a linear classifier not be used? The simple reason is the actual data patterns which an actual email spam would have are not as simple as what is shown here. So a linear classifier would not work in such cases. For example, I'm giving here now a clear illustration of what we mean by the earlier observation that an adversary would try to influence either the machine learning training, model training, or more importantly, the later part, adversary would try to give such data which would cause the machine learning model to fail. Remember earlier I called it as exploratory or evasion attacks, although the details of that I am yet to talk about, but I just hinted at these two terms. And here is a clear revelation of what adversary would do. And that is discussed in this particular paper, Machine Learning for Email Spam Filtering. It's a beautiful paper which talks about different machine learning approaches for email spam filtering. Let's say I may use neural network, I may use decision tree or decision forest, I may use SVM based classifier. So I would use different machine learning models to algorithms to build my spam filter, and then it talks about what are the weaknesses of that spam filter, how it could be attacked. Here, what I'm trying to talk about is what would adversary do? So adversary would have, look at this now this right side diagram, adversary has still that particular term which he wanted to propagate. Bi is equal to 1, Viagra is equal to 5. But now in order to befool the model, remember earlier I had used the term adversary would give such data by which it is able to befool the model. Adversary would use a term like conference, would use a term like meeting, for which over a period of time, by carrying out repeated attempts, adversary knows that the weights which I have attached to these terms are low, because I am considering as a spam filter designer, I am considering that mails which contain the term like conference or meeting cannot be a spam mail. They are important mail for me. So the weights given here are -2 and -3, which adversary has been able to learn over a period of time after repeated attempts to break the model. So he would include these terms in the mail. But what is the result of this? Remember that linear classifier. Because linear classifier would behave on a strict line or on a plane and try to summate the scores and see what is the overall score and compare it with threshold. Here, if you try to do 1 plus 5, which is 6, minus 2, which is 4, minus 3, which is 1, I get the total score. Even though the mail contains the term by Viagra, the total sort of score which comes out is conference meeting. I mean, it comes out is 1 because of the benign terms introduced by the adversary in the mail conference meeting. So because 1 is less than the threshold which has been set by the spam filter, this mail would not be classified as spam by spam assassin filter. Remember I said earlier, one of the most popular, the spam filter which is known to be a very powerful spam filter, which is this spam assassin. Even this filter would fail in such cases because it is using a linear classifier. That's why I raised the question here. Can such a classifier be used with for spam filtering in presence of adversarial machine learning? So we conclude that such a classifier cannot be used, which is based on adding some good words in order to befool the machine learning model. And therefore, whatever was spam would not be classified as spam. In that sense, the noise, now try to recollect what I was trying to mean by the term perturbation, which I used earlier, or by the term randomization, random noise, yes, instead of stochastic, I tried to use calibrated noise earlier. So random is something which is not in your control. But what would you say about this conference meeting which adversary has deliberately induced? That is under control of adversary. So the model which we have now is something like this. Instead of noise remaining a random noise, it is no longer now random noise. It is the noise controlled by the adversary. Something which is controlled by the adversary would behave as per what adversary wants, and that would lead to failure of the model. So this shows now at a deeper level as to what is the genuine cause, what causes adversarial machine learning to happen, what causes adversary to succeed in attacking a machine learning model. The basic reason is that many of the machine learning models, you may have a question here. You would say that why should I use a linear classifier? Well, the basic reason for that is many of the machine learning systems, when they were built, when they were designed, when they were deployed, it was not anticipated that they could be used by an adversary for his advantage. They could be maliciously used. So because of that reason, the system simply focuses on quick use. It only focuses on performance or efficiency of usage. It doesn't focus on withstanding the adversarial attacks. And that is the reason why this field has come up. So I think I explained this earlier. The two models, the Shannon's stochastic theory or random noise theory versus the adversarial noise theory, which is given by Hamming. And the details which are shown here, I'll not read them because I think I have tried explaining them. And I'm saying these are the summary of the inferences. But I'll have one more view on this by means of a beautiful diagram which appears in a textbook. You can see the name of the author on this right hand side top screen, Clarence et al. So that's textbook is one of the rare textbook which talks about, the title is Machine Learning in Security. So I'm giving that as a forward pointer to you, worth studying in order to understand how this entire thing happens. That is what is given here. The analogy which the author gives in the book is that of a swimmer who is trained in swimming pool, a machine learning model which is developed without adversary into mind, and that swimmer is now asked to swim in sea. He'll not be able to swim. Exactly the same thing happens. The model, which is innocuous model developed using stochastic noise theory, has now been asked to be used in presence of adversarial data, and that it would not be able to withstand. So I think I'll not go into this. And the fundamental problem, therefore, is imperfect learning. That imperfect learning is because the data which was used for training the model, that itself was faulty data. So I said I'll show a beautiful diagram. I'll not go into this, but we'll show a beautiful diagram, which is this diagram. So what it talks about is the Bayes error rate is known in machine learning, which is the lower bound on the possible error for a given combination of statistical classifier and the set of features we used, which I explained earlier. What are the weights associated with different features? The confidence was -1 and meeting was -3 and buy was 1 or something like that. So Bayes error rate would say that if at all, I am not considering all the data which may occur, there is going to be certain problem in my learning, and I would try to take care of that in my machine learning model. But adversarial space is something which is training data drawn from a theoretical distribution space which is deliberately introduced. So look at this right side. It says there is some training data distribution, there is some test data distribution. We know that test data distribution is going to be smaller as compared to the training data distribution, and there is going to be some difference between these two. But that difference now is controlled by the adversary. So that's what is shown here as what is shown in blue is adversarial space, which is controlled by the adversary. And if that is used during testing phase, then you would assume that your machine learning model will not work properly. So when evaluating the model in the lab or in the wild, the test set, which was drawn from the test data distribution, may contain a segment of data whose properties are not captured during training of the machine learning model. And because of that, the machine learning model fails. So these blind spots are actually exploited by the adversary. So I'm trying to give you, some foundations on what the adversarial machine learning rests on. So I'll skip this particular slide, which talks about imperfect learning. I explained the cause of imperfect learning earlier, or model poisoning. I explained what is model poisoning earlier. There is one more concept which is related, and that is attack transferability, which says that which is more catastrophic. I'm saying it is more dangerous. Why? Because if adversary is able to learn from his attacks which occur on a particular model, and if he is able to successfully transfer them to some other application or other model, because the data characteristics are similar, then that is even more dangerous, because even if you safeguard that other model carefully, the adversary is going to be successful. Okay, so adversarial, that's what it says. Adversarial samples which are drawn from adversarial space I showed in a previous graph, which are specifically designed to cause a misclassification in one model and are also likely to cause misclassification in other independently trained model, because there is some relation between those two data. And this can happen in any sort of security application very commonly, because if you think of, say, antivirus software, which is using some of the known features in order to tag something as a virus, and a network packet which will have some of those things introduced in that packet to attack a site. So the data features are going to be related. Adversary would use them to create data on some other model. That's what it says. Even when the two models are backed by distinctly different algorithms or infrastructures used for training them, adversary would succeed. So attack transferability is another danger in case of such systems. I'll skip them. I'm showing here the growing research interest. It is that if you look at the title of the paper, the title of the paper is related to healthcare. So you may wonder as of now that the title of the talk was adversarial machine learning in healthcare, but I'm nowhere talking about healthcare. The reason simple is whatever background material I've talked about that applies to any security application applies to healthcare applications also. So that's what you see here. The survey on adversarial attack and defense for medical image analysis. I am using this paper. I mean, it appears in a very renowned journal, ACM Computing Service. The paper is also relatively recent paper, March 2025. But what it shows is the growing interest in the community. So starting from 2018, the number of papers which talked about either adversarial attack or which talked about adversarial defense, that is growing. You may observe here that perhaps the ways to attack now is decreasing, because researchers also would be studying the adversarial capacities, capabilities. It's not that only when the attack is orchestrated by an adversary would everybody in the world would be able to know that such is the method to carry out the attack. That would be studied by researchers also. So you could see one positive aspect here is that the number of papers which talk about adversarial attacks has slightly reduced, but that is only up to September 2024. So the data after that is not available. I mean, it's not shown in this particular paper, I would say. It might be available, not shown in this paper. But if you look at the mitigation techniques, adversarial defenses, blue lines. So you would see a number of research papers published which talk about the defense mechanisms for these adversarial attacks, which means basically is a proof of the fact that there is growing interest in research in this particular area. Okay, now I'll briefly talk about the modeling of the adversaries and the types of attacks which I mentioned earlier. So I'll not go into this diagram. Basically, it talks about different ways of attacks. We are going to talk about 4 of these attacks here, what I am trying to show using my cursor scrolling. And on right side, it shows defensive modeling. So if at all, I think the time would not permit, but I'll have those things included in my PPTs, which I'll share with you all. If at all the workshop FDP organizers are going to share the PPTs. So what are the defensive techniques that also would be included therein? I might not be able to talk about them. I think I've explained what is adversarial modeling. I talked about types of attacks which can occur. And the other important aspect is what is the attack surface? The study of the capacity of the attacker, what all attacker can do. The study of what is the goal of the attacker, what he wants to achieve. The study of the attack surface on my system, what are the weak points which the adversary can exploit and attack my system. Study of all of those is basically a modeling of the adversary. So let us look at a diagram to understand what is this attack surface. I'll simply go to this particular aspect. I'll come back to this, some of the slides slightly later. Let me come to the attack surface first. So look at this diagram. This diagram is for a typical self-driven automated vehicle system, which is basically a self-driven car, which is machine learning enabled. We obviously know that this car should be able to detect a stop sign, stop traffic sign automatically. It would be trying to take a snapshot of the stop sign using a camera. This would be processed. There would be a 3D tensor. Apply that to machine learning model and determine the class probability. So the machine learning application in this self-driven car would be trained in such a way that it would be able to identify this sign as the stop sign, and so the car would stop. Remember, I came to this slide because I was trying to tell you what do we mean by attack surface. So adversarial machine learning researcher would say that all of these points are the attack surface of the system. Adversary can either play some foul on the camera when the traffic signals are being given input to the system, or it could attack this data processing part of the entire system, or look at the model wherever the 3D tensor is applied to the machine learning model, attack that part, or could give a wrong sort of input here when the model is actually going to do classification, adversary would give an input for which the model is not trained. So model would not be able to know, detect, predict what is to be done, and would not be able to identify the stop signal. In fact, I have not included that in my presentation, but there are papers. When you read those papers, people have befooled these models in such a way that a stop sign has been identified as a panda, an animal. So that is even more dangerous because an attacker is not able to carry out an attack to say that the self-driven car would not be able to detect a stop sign as a stop sign. Remember that perturbation which I talked of earlier. Differentiate between stochastic, which is random, and I use the term calibrated or perturbed or adversarial noise. These were the terms used then. What is adversarial noise here in this context when we are looking at the concept from attack surface point of view and from trying to understand the adversary's capacity? For this use case, what adversarial noise would mean that the adversary is able to give that input to the system so that the stop sign would be able to adversary would be successful in making this model predict this stop sign as a particular animal which adversary wants. So that is what we mean by calibrated noise or adversarial noise, something which is in complete control of adversary. Otherwise, what could happen is adversary would simply befool the system so as to do not predict it correctly. Stop sign would not be identified as a stop sign. That would be the goal of a limited capability adversary. But as I said, papers have been published which basically show that the model can be befooled to this extent also. And there are some interesting observations, interesting collections on those papers. The pointers to which you are able to see at the bottom of my screen, there are interesting attacks presented. Some heroine of the Hollywood, when her image was shown with a particular badge worn by that image, that heroine was predicted as somebody else, some other person. That is the extent to which the adversary has been able to influence the data. I mean, all this work done in research in order to show the capabilities of the attacker. But coming back to the original question, we were trying to talk about attack surface. What do we mean by attack surface? So for my ML application, what are the probable points on which an adversary can carry out the attack? This is a beautiful diagram which talks about the attack surface and compares attack surface for two different applications. One is network intrusion detection, which is machine learning based. Other is automotive computer vision, which is obviously machine learning based. And third is shown as generic machine learning system. Why I said this is a beautiful diagram, it shows that for a generic machine learning application, what are the operational components of that machine learning application? Like, there is an object, there are some actions, there are sensors or camera or IO hardware, converting them to bits, digitize those, do some pre-processing, noise removal, identify features, apply features, use those features with the model, apply the model, and do whatever is to be done as machine learning task, classification or prediction or regression, whatever it is. And then take some action in physical domain appropriately. The same thing has been mapped onto automotive computer vision. It is mapped to network intrusion detection. So the theme is that the machine learning application, it will follow the similar phases. Only thing is the entities, the objects of interest would differ. In case of computer vision, it could be traffic sign. In case of network intrusion detection, it could be network traffic. But ultimately, the adversary, that is what I was trying to talk about earlier as attack transferability. The adversary who learns from a particular application would be able to transfer that attack to some other system because the attack surface has more or less remained the same. That's why it says generic model and generic sort of attack surface also. There is one more diagram which tries to talk about the attack surface for the system under consideration, healthcare. So what are the typical use cases of a healthcare application, which is machine learning based? So machine learning in clinical workflow, that is taken as the healthcare application. It says whatever is shown by this points, Those are the points where the attacker would be trying to carry out the attack. So the title is appropriate, AML surface in a healthcare application. What I skipped earlier, so that was the first component. I'm talking about modeling the adversary, and modeling the adversary is trying to know what is the attack surface, where my system can be attacked, and then trying to know what are the probable types of attacks. The types of attacks now, perhaps it would be easy for me to convince you because I have already mentioned them somewhere earlier. The third is the goal of adversary. What are the goals of adversary? And the fourth component also I mentioned. Goals I have not mentioned earlier. I'll mention it slightly after a moment or two. But capabilities I mentioned. I said adversary capability could be either it is an insider adversary whose capabilities are much more stronger because he's part of the system, or an outsider adversary who is outside the system and so his capabilities are lesser because he cannot have access to training data. He cannot influence the training. Okay, that is the adversary capabilities. If you see earlier, and if you look at these diagrams, the taxonomy or different ways to understand the attacks, I'm deliberately showing a different number of papers to talk about how attacks have been studied. So, and the title of all of them is the same, taxonomy of adversary attacks. But these taxonomies, they revolve around what I just explained. So the adversarial attacks based on the knowledge which the adversary has, which gives rise to something which is known as white box or a black box. And now you would immediately be able to relate this with capability. If I say white box, the adversary capabilities are higher because he's part of the system. He's able to see the system. He's able to influence the training model also. So that would be white box. While a black box would be an evasion attack which would occur during the deployment phase of machine learning system. I talked about a self-driven car where a red sign, stop sign signal is detected as a panda because adversary is able to give such perturb input during deployment of that application that the self-driven car identifies that signal as a panda. So that would be adversary having limited capabilities, but able to generate an input which would cause evasion attacks. So that is what is another type of attack. When we talk of the attack classification, if you look at this different diagrams, you would have all these terms included. Whatever I mentioned, they would be included, except for one thing, wherein I did not mention what are the goals of the adversary. That I am yet to talk about. From all these different taxonomies, I prepared one taxonomy here. If you could figure out, drawn in PowerPoint, but it basically says that I should try to study attacks from the knowledge perspective of the adversary, what knowledge it has, the specific goal of the adversary, whether goal is targeted or non-targeted. If you think, I gave an example of a targeted attack some time back. I said that red sign would be detected as panda, so specific target of the adversary. Adversary is not simply wanting my uh, uh, self-driven car system to fail. He wants that self-system car to fail in a particular manner. That is what is targeted. So that is what is known as adversarial specificity or the type of the attack. So whether attack is on some security or is trying to influence the model or is influencing the data or so on. So therefore, many of these classifications are interrelated. The frequency of the attack, whether it is one-time attack or iterative attack, whether it is generating a false negative or is aimed at generating false positive, that is adversarial falsification. So combining all these different diagrams, the general taxonomy, general attack types which one should study are shown in this particular diagram. I have cited this, actually it's wrong. It's drawn by me in PowerPoint. So this citation is a mistake actually. So that leaves me with talking about the goals of adversary, and the goals of adversary are shown here, which is pretty simple to understand. Either the goal is the goal of the adversary is aimed at confidence reduction. So if my model is going to do some prediction, then that prediction would be done with lower confidence. Naturally, that would be done by an adversary which is less powerful, which doesn't have access to the model, which doesn't have access to many of the parameters used in my model. So at a very low end, confidence reduction would rest. It could be misclassification. Now I'm interested, I have some more information as an adversary. So I'm interested in causing the system to misclassify a red sign classified as a panda, or it could be targeted source target misclassification. I am trying to target either the source or I am trying to target the destination, and I am using this classification with a very calibrated view that a particular entity classified as particular something else only. Misclassification is a weaker form, this is stronger form. And just as we have source target misclassification, the most strongest form of the goal is targeted misclassification, adversary wanting classification to be done in a specific manner. I talked about a heroine in Hollywood being identified as a separate person. So that is what would be targeted misclassification. Attack surface I already talked about. This also I talked about. So then I am showing different, study of this basic attack types in adversary, but I'll not go into those. You can refer to them in the PPTs because I have already tried talking about these attacks. I have not talked about security violation, but anybody from security field would be able to know what are these attacks. I am showing integrity attack. So attack taking place on the data of ML system, that is data integrity or entity authentication attack. Attack taking place on the availability of the system. So these are all security attributes, or attack taking place on the privacy of my system. So those are categorized as security violation. I talked two terms earlier, poisoning attack and the evasion attack. And that is what you see here in this diagram. When I say causative attack is poisoning attack. Poisoning of what? Poisoning of training data. So an insider attack would be causing causative attack. He would be able to maliciously influence the training data in such a way that the the model would not perform properly. That is what would be considered as causative attack. And so the term which I used as data poisoning is the same as causative attack. And the other term which I used was evasion attack, which is same as exploratory. Evasion would be taking place during deployment, and that those are known as evasion attacks. So I've tried explaining those here. Very simply, to keep these in mind, we would say evasion attacks occur during testing phase, while poisoning attack occur during the training phase. And this diagram again from a paper beautifully talks about the two different attacks, like what is taking place during training, what is taking place during inference or deployment phase of the machine learning system. So I'll skip all these slides. Okay, this is a typical uh, real attack which illustrates what is poisoning attack. It's an exercise which I give to my students. I mean, simple exercise to sort of make them interested in learning more about these attacks. So it shows a simple sample bank application, which is the credit scoring algorithm, machine learning based credit scoring algorithm used in a bank. And it says that this is the training data used in the bank. Uh, Obviously, if we talk of poisoning attack, this attack would have occurred during training phase. So adversary would have been able to insert such malicious samples in this that the model would give a particular credit score when a particular feature is satisfied. So what I'm trying to point out, the question is, can you spot anything fishy? I mean, all these patterns are to be very carefully studied, but I'll straight away give the answer. And that is, if you look at the age, in all those cases where age is 30, the credit score is something. It is in a particular range only. Suppose the credit scoring algorithm says that any score below 700 is not acceptable. If that were the case, then with 30, you are able to see the credit score as 784. Again, when the age is 30, you are able to see score as more than 700. Again, when the age is 30, irrespective of what the profession is, whether profession is teacher or a lawyer, or here again it is teacher, here it is again lawyer. So whatever the profession may be, as long as the age is 30, the credit score always goes above 700, which means this credit scoring algorithm has been influenced in such a way by the attacker that uh, with age 30, it would always give positive credit score to the user in case of to the customer in case of this bank application. That's what we mean by poisoning attack. And that's where we say that the capability of the attacker is greater. That's what we call as the white box attacks. I have my slides till now have not shown the white box, but that's what we would say white box, because the adversary is able to get in, is able to see the entire system. These things I think I've, the email spam example which I gave earlier using the terms buy and Viagra as the spam terms has been shown using some other terms here, but the basic objective is the same, the threshold score and the linear classifier. And we would now consider, in order to better understand the illustrations of evasion attacks and poisoning attacks. So this you should try to look at and note that this is the example of poisoning attack. Comparison of evasion versus poisoning. I'm saying this is an poisoning attack because I have modified or manipulated the training sample. As compared to that, the evasion attack would be given here. The adversary was not able to get access to my training model. Adversary was not able to insert terms by which a particular mail would be considered as spam. But when the spam mail was generated, adversary inserted certain terms in the spam mail. So that is why this attack is occurring during the deployment phase. The Joy Oregon, which is considered here as negative, but cheap mortgage, which is given positive. So this negative is the term which causes my spam filter to fail. These terms were introduced during the execution phase, and therefore we would say that this is the example of evasion or exploratory attack. So I think I have tried giving you a clear understanding of the attack taxonomy. There is a formal sort of denotation of the attacks, but I'll not go into those. This diagram tries to talk about the white box or black box attacks. It also gives something like gray box, but the meaning is something seen in this diagram itself. The training backpropagation, inference backpropagation, what all information adversary has, that classifies. So we just have to look at the white box and black box, and we would say that in case of white box, adversary is able to get access to training, which is what I said as the white box, greater capabilities of the adversary. But black box is where he has a sort of hand on, he's able to influence only the query which is given to the system and not to the other accesses. So it is black box attack. That is what is explained further. So I think I am left with how many minutes? 5 to 7 minutes. If there are any questions, I would take those questions as compared to going further in this. Is it fine with everybody? I'm showing certain diagrams, certain characterizations of the adversarial attacks here in this further diagrams. Like, if you look at the relation of white box, non-adaptive black box, adaptive black box, strict black box attacks with the capabilities, then they are shown to be in decreasing capability, which I think is pretty intuitive to understand. I already said white box is where adversary is able to have access to everything. So it must have higher capability on the part of adversary. If you look at the complexity, white box here stands on terms of, uh, confidence reduction. Then you have misclassification, targeted misclassification, and source target misclassification. So if you look at only these four, then on this side, the complexity increases because confidence reduction is the simple thing to achieve, less complex. But as I go on making source target misclassification, it is increasing complexity. So both these terms are related here. Increasing attack difficulty is the overall result. And this is for the uh, the evasion attacks. The same thing, whatever was in terms of white box, black box, would now go to, in case of poisoning attacks, as logic corruption, my model is being influenced, a data modification, which data used during the training phase, or data injection. Either I modify the data or inject some new data into the training samples. So that is what is again decreasing capability of the attacker, but applies to poisoning attack. So some of the beautiful diagrams which basically talk about attack modeling. Let me now try to talk and show that paper which I was talking about, which I tried generating your motivation from. So this is the paper which I was referring to, IEEE security and privacy paper. If you look at the bottom footnote, it says adversarial machine learning industry perspectives. And as you could see, I told you earlier, I made a mistake earlier. I said it is written by people from both Google and Microsoft. It's written by people from Microsoft only. As you could see in the email addresses, all of them are Microsoft email addresses, but they have given perspectives of all the industries. So they have tried talking to all the industries, and they have given what each industry is trying to do from whatever information they could gather with respect to adversarial machine learning. So the title comes out to be this: slightly older paper, 2020, but most of the things presented are good pointers today. Uh, so that is the paper which gives pointers to what I talked about earlier. Given so many instances of the attacks which are modeled in research papers, different research papers published by the researchers in adversarial machine learning community, which would span any domain, even healthcare applications being mentioned there, which basically show how the researchers have been working on the adversarial machine learning concepts with the use cases in different areas. Use cases go into the area of, so one may say, one may raise a question that does it apply only to image processing? Because many of the examples I gave were related to detection of images, but it goes into the audio examples also. In fact, they were able to generate the voice of a particular person using these adversarial samples. So that is what we would call as targeted misclassification, one of the attack which we talked about earlier. And which attacked, they also took examples of the perspective of the industry, which attack influenced a particular organization the most in terms of distribution from 0 to 10 on a scale of 0 to 10. So you could see different things mentioned there: poisoning, model stealing, or inverting a model, or inserting some backdoor into the ML model, inferencing from the membership inference, or generating an adversarial examples. I have not talked about all the classifications, but in the paper they are talking about all these different examples of the attack adversarial modeling, and they are trying to say which attacks have been the most frequent attacks which your organization has experienced. That's why it is industry perspective. Uh, those in security domain would know the OSP site. It is basically uh, a kind of collection of the weaknesses which have caused a particular attack to take place. So such vulnerabilities are shown, such attacks are shown for normal security application. Similarly, in machine learning security, what are the attacks which are top 10? Every year it is published. The data which I am showing is that of 2023, slightly older data, but that at that time, amongst the machine learning attacks in adversarial machine learning, what were the most frequent attacks? So you would see data poisoning standing on top in both the cases, this industry perspective also, and here also. So quite an interesting thing to learn about. There are some of the questions which you should try to answer based on whatever I presented earlier. As I said, this is not end of my presentation. This can continue further by looking at what I was talking about in the first slide, where I said, if I go to the content slide, let me go to that. We could talk about what are the generation strategies, how these adversarial data samples are generated. We could talk about what are the defense strategies. So defense strategies are coming from the security domain as such. Uh, uh, Training the model with, okay, so in defense, I would make a mention of only one very important aspect. I have some 1 minute. Pardon me for slightly exceeding, but I would give one very simple example of what could be the defense strategies in order to show you pointers towards that. Many of you would have heard of generative adversarial networks as a deep learning technique, and why it has come to the fore recently, why it has been accepted as a very important aspect of study. Because a GAN would consist of two neural networks. One is what is known as a generator, other is known as discriminator. The task of generator is to generate adversarial samples. What do we mean by adversarial samples? The samples which would cause the model to fail. So that is exactly what is adversarial defense. In adversarial defense, the system would be trained to generate those samples which may come from adversary, which is now is the task of one neural network known as the generator. And what would the other neural network do? Discriminator. Discriminator would try to discriminate whether this is a valid sample or invalid sample. Thereby, you are able to make your system defend against what would be generated by the adversary later on. So I think if you look at the basic working of GAN, that's the best example of what could be an adversarial defense. Otherwise, many of the other techniques, they come from security domain, and I would not go into those things. So that is how I would summarize my talk. I would welcome any questions if at all they are. Over back to you for further discussion.
Participants can ask the question. Any question from participants?
Hello.
Oh, yeah,
Yes.
please.
Yes, sir. I have one question.
Please.
Online, like OSF website, we have a data that is available on website on OSF. Okay.
Mhm.
So
Mhm.
if that data is available, we download it and we are doing machine learning and we train the model and we get a testing and also testing and we are not getting a good accuracy. If data is manipulated on OSF, how can we get testing accuracy, sir?
No, that is a
How
basic
to
machine learning
identify?
problem. No, that is
No,
basic
sir.
machine learning problem because we know the
Yes, sir.
efficacy of a ML model that would always
Yes.
be dependent on the data which you have used for training and testing. So the
Yes,
problem
sir.
which you are talking about is the poor
Data
quality input
manipulation.
which you are using. Poor quality input which you are using. If you say that I am downloading something from somewhere, that means it's a data set problem. It has nothing to do with adversarial machine learning. So try to
Okay.
understand one thing. When I say adversarial machine learning, what I am referring to, I have used genuine data. I have used proper data set for developing my model. Once I have developed it, I am sure it would work properly, but then it doesn't work as per my expectation. Why? Because adversary has come into play somewhere in between.
Okay, sir.
So that is the distinction between the two. Try to understand. And that's what I said earlier, that most of the machine learning systems have been developed by assuming that the data which is used is not going to be manipulated by anybody. Am I answering your question?
Yes, sir.
Okay. Any other
Anybody?
question?
Thank
Okay,
you, sir.
fine. Thank you.
Okay, sir. Thank you, sir. On behalf of the every. Hello. Any question from participants? Okay, sir. Thank you, sir, for on behalf of the every participant. Your presentation has given very deep understanding of the challenging and solutions in securing the AI systems. And we truly appreciate the depth of your knowledge and clarity with which you presented the complex concept and real world relevance of your example. Thank you, sir.
Thank you very much. Thanks to all the participants.
Okay, thank you,
Thank
sir.
you, sir.
Yeah.
Now our next expert, sir, is Dr. Kalyan Sasidhar, sir. Welcome everyone to our second session of the day. Now it is my pleasure to introduce our distinguished speaker, Dr. Kalyan Sasidhar, an associate professor specializing in mobile and pursuing computing, including wireless sensor and mobile phone-based sensing. Dr. Sasidhar completed his PhD in computer science from University of the North Texas in 2011 and pursued the postdoctoral research at Young Technology University, Singapore. He has also served an assistant professor at Amrita Viswa Vidyapeeth, Kerala, with over 25 high-impact publications and more than 650 citations. His research on indoor localization, context-aware computing, and mobile sensing has a global impact, and he has presented a leading conference, including IEEE, Postmates, and IEEE ENTS, and continue to inspire students and researchers like his work bridge cutting-edge research with real-world application, and he has made a significant contribution to advancing smart mobile technology. It is my honor to invite Dr. Kalyan sir to take over the session and share his insight with us. Now, welcome, sir. Hello, Kalyan sir. Hello. Kalyan sir has a problem of mic, so he will start. He will soon start presentation. हेलो, बस आपने ज्वाइन किया सर? ओके, हाँ सर, हाँ नहीं सर, ज्वाइन है तो मुझे बता दे तो मैं आपको प्रेजेंटर बना दूं, ठीक है ना सर? ओके ओके, थैंक यू सर। ओके, या नहीं कोई बात नहीं सर, कोई बात नहीं, आराम से सर।
Hello, am I audible?
Yes sir, you are audible sir. Hello. Now we can sir present.
Okay, great. Let's see. Share. Okay. So my screen is visible, right?
Yes sir, your screen is visible and your sound is audible sir.
Great, thank you. Yeah, very good evening, all of you. Firstly, thank you, Dhaval, and on behalf of your institute for inviting me for this talk. This is the first time I'm actually giving a talk around this time. So thank you for keeping me active even around 7:30, 8 o'clock. So welcome all the participants. I wish it could have been a physical presentation so I could see and work with you guys, interact with you all. So, and yeah, firstly, thank you for the introduction. I'm yet to make a strong impact in the academic research world. I'm still not there, but I'm doing my best. So I've been working in this area of mobile and pervasive computing since 2008 or 9, since my PhD days. So the topic of this talk today is development of an affordable and accessible wearable device for gait assessment. So let me first tell you what we're going to be discussing or learning today is I will give a quick introduction or sort of discussion about what was there before the wearable era started, maybe a few years before, and then we'll start from there in terms of what were used to sense data, what were used to collect data and analyze, And then we will get into the wearable device trends in terms of market. For example, I won't touch a lot about research because the scope is too large, but I'll give a couple of examples of where we are. And then I'll get into the motivation of our project, why we came up with that. And we have been working on this project since 2 to 3 years with a bunch of students. And I also have my student, MTech student Parikshit Joshi. You're there, right, Parikshit? Yeah, I'm sure he's there. We'll then talk about how we designed this device, including the hardware and the the enclosure, how we made it. I'll tell you why we did that. Then we'll quickly get into the methods as we used to collect data, what kind of data was collected, what analysis we did, and I'll conclude the presentation. So this cartoon diagram gives us some hint of where we were a few years ago and where we are. So the one on the left shows a person wearing a smartphone. It's not clear, but it's big. So it's a smartphone on his wrist. You may have seen the pouches which people used to wear on their wrist, and they would jog because a smartphone could do certain things, like it had a pedometer application which could count the number of steps. So they used to wear it on the wrist and then they would run. Fast forward to the current era, or the last maybe 5-6 years majorly. Although this cartoon, this lady is wearing still a smartwatch, but look at this person. He's wearing a smartphone. He's wearing a smartwatch. So there's no phone anymore. You need to wear. That is completely replaced by a tiny device which just fits on your wrist, and that's the smartwatch. And I'm sure many of you are actually wearing that smartwatch right now. So this is a transition from a smartphone based health information system to a smartwatch which is way much smaller than a smartphone, and also size wise, also weight wise. So you don't need to carry your phone anywhere. So what was that happening before? So this whole concept of sensing data using smartphones started way back sometime around 2007 or 8. So if you see this graph here, it shows how the sales in smartphone went ahead. I did not want to add research part of it, but even in research, if you go back and see Google Scholar, the trend started sometime around 2007. Why? Because that is when smartphones or mobile phones transitioned from the brick Nokia phones which we all used to have to a big screen, 5-inch screen. The one on the left right here was the first ever smartphone by Google, which ran Android version 1, and it was from LG. They called it LG Nexus 1, I think so. I forgot the name. So I was lucky to have this phone with me through my professor's research funds. So it was fascinating. I mean, you could slide the screen, you could type, and then slide the screen back, and then the screen was somewhere around 4.5 to 5 inches. But that's not the point. The point was these phones had sensors inside them. The sensors were embedded inside them. I'll tell you what sensors they were. And so gradually what happened is the phone started to become or move from a tool which was just used for making calls, receiving calls, sending text messages. Of course, there was no WhatsApp those years, right? So it was changing from becoming a simple communication tool to a sensing tool. You could use those sensors to sense some data, of course, by writing some programs in Android, some code. And then you could also do some amount of computation. Some calculations could be done on those phones. So the phone became a sensor in itself. You did not need any other external sensors for certain applications. So then people started to explore, like anything, the research academic groups, looking at active versus passive sensing. You just leave the phones, or you carry the phones in your pocket. They are already sensing right now, right? So those mechanisms were developed by researchers, and one specific application or problem that we were focusing was indoor localization using smartphones. So how can I locate a person when he gets into a building using these sensors and then track and navigate him. So it becomes a system very similar to GPS outdoors. So the advantages became huge. So many benefits of using smartphones as sensors. One of the major advantage was something called crowd sensing. So if I just ask all of you sitting there, around 170 of you, let's assume you have an app that collects data, which we have built. So I just say install this app, start the app, and then let it run background. It's not going to disturb you. It won't collect any private data. After 1 week, if I get back the data, I can understand what kind of mobile apps you use, how long you use your mobile apps, how much of movement you have, where do you go from point A to point B, when do you sleep, how long you sleep. We can extract all of these things. That has been my work since the last 4 years. So it became a crowd sensing tool. Crowd could sense the data for us and give. I don't need to go and collect data. So the sensors in the phone included accelerometer, gyroscope, the compass was there. We know what a compass does. It also had, of course, camera, microphone, magnetometer, Wi-Fi, GSM radio, so on and so forth. So people started to use these sensors to capture various physical quantities outside. So with camera, we know what you can capture. With microphone, you could capture sound. With Wi-Fi, you can capture signal strength values. You can also capture locations because Wi-Fi is connected to an access point. Access point has its location. You could use a light sensor to capture the surrounding light and do lots of interesting things. But the important sensors we were focusing were accelerometer and the gyroscope. So your accelerometer, unlike the accelerometer in our vehicles, it's not the accelerometer sensor which accelerates, so on. This is a simple force measuring sensor. Okay, so I'll show that working of that sensor. So what did people do is people use this sensor to do various kinds of analysis. Okay? One of the analysis that is of the theme of this topic is gait assessment or gait analysis. So what did people do? They wore the watch, the phone around the waist. This is an iPhone. You can find the link here. Okay, they fixed iPhones in a band and they wore the iPhone around their waist and then they walked. Because iPhone has an app that calculates the steps. You can understand something from that. Similarly, this is from our paper. I'll show that paper in some time. We fixed another smartwatch near the ankle and we captured a lot of interesting parameters to analyze and do some classification, which I'll talk about in detail. So the wearable technology grew gradually from around 2017, 18, and smartwatches were the ones to start. We could see smartwatches in the market, simple smartwatches, and then gradually iWatch, and then you have Board, you have all of these watches. So majorly it was if you see the statistics on the right, the global wearable market is all about the wrist. So there are hundreds of companies that are only focusing on smartwatches. Right? In India, you can buy a smartwatch for 2,000 rupees, even 1,000 rupees, so you can go and buy an iWatch for 25,000-30,000 rupees. So the spectrum is there. There are hundreds of so many companies. It's become so easy to make now because the availability of sensors, microcontrollers on a small scale. Very few companies are looking at wristbands. Okay, you have rings also now, smart rings. Some companies have started that, but the major growth, the capturing in the market is by smartwatches. Right? Smartwatches have limited capability except the iWatch. Most of the smartwatches can count the number of steps. They can tell you your calorie that you burnt and maybe a few things. But your iWatch can also tell you your heart rate, it can tell you your BP, it can also look at your blood pressure and so on and so forth. Right? I will not touch on the technology that goes behind them. So these are some statistics to give you some idea about smartphone, the different sensing methods from smartphone based sensing to smartwatch or wearable based sensing. Okay, so we started to focus on healthcare, especially to understand gait. I'll tell you what gait is. And then we wanted to see, can we build a very simple device that can do something? Okay, it is not that there is no other device like this in the market. There are a huge number of wearable devices proposed by researchers. There's hundreds of publications on wearable gait analysis, wearable devices. But the important point is that for India, for healthcare, there's no such device. We did a lot of user research, market research. We went to nearby primary healthcare centers, physiotherapy clinics to understand what is the state of the art. They don't have any wearable technology for healthcare, especially for gait. So that brings us to the question of what is gait? Okay. So gait, I'll just read that definition. So in simple, gait is nothing but your walking pattern. Each one of us has a different way of walking. We might look very similar, but we are not similar. The way we walk is very different. So gait is the act and manner of walking, but then it is basically consisting of a complex motor skill, right? You have your limbs, they have to sync, they have to coordinate. There is some symmetry, which means there is a cycle how we walk, the right leg, left leg, and so on and so forth. Although it can be performed automatically without any effort, gait requires integration of mechanisms of locomotion with that of balance, motor control, cognition, musculoskeletal function. It's very complicated. Your brain has to coordinate, your muscles have to coordinate, your skeletal systems have to coordinate, your bones, the leg bones, everything, they all have to sync to help you move. So what is gait analysis? Right? I will quickly open this video, but I will not, let you watch the entire video. I'll just fast forward to quick places where I can show what gait analysis actually means. So this person is walking on the treadmill. Okay, I've muted the thing. We'll just look at this. So I'll just go back to this. Yeah. So we'll just look at what is a step and what is a stride. Okay. So when you walk, the first step we do, it's pause there, is when you hit the ground with your heel. So that is the first step. We call it heel strike. Your heel is striking on the ground. Then the next foot comes. Like you lift and then the next foot comes. Then this one action of one leg heel strike hitting on the ground and other leg moving is called a stride. So one is a step and the other, these two are strides. Okay, so and then it ends with the initial contact. So you have two steps, but then you have one stride. So now we look at something called a cycle of gait, and then we'll see two very important phases in the gait cycle. One is called a stance phase and one is called a swing phase. So what is the stance phase is, it is basically taking up most of the part on your way in your walking. The right foot is always in contact with the floor. It's alternating between right and leg, up and down, up and down. So that phase of your walking is called the stance phase. Okay, the right foot is always in contact with the floor, hence it's on stance, almost like hitting. And in the swing phase, which makes up 40% of the gait cycle, okay, the right leg is swinging. If you see the other, this leg or the that leg, it swings. One is sort of on the ground, the other one is swinging, the other one is swinging, and so on. With heel strike, the leg has to accept the weight of the body, right? When you're hitting the heel, this entire leg has to take the entire weight of the body. This is called loading response. Okay, so that's it. I will not go further into this. So coming back to this diagram here shows us the gait cycle. Okay, what does the gait cycle basically comprise of? Like I just said, the heel strike. Okay, then the other leg moves. So while the heel strike is happening, you're trying to put the weight on your body. So that's a loading response. And then there is the next leg that moves. And then this leg stands and next leg is moving here, which is called mid stance. And then you have your heel off, the heel goes up and the next leg comes. So this is supposed to be a cycle. Okay, and that cycle stays until 60% of your gait time. Let's say you walk for 10 minutes, 60% of the time you're around that percent. 60% of the gait cycle comprises of the stance phase. The next phase is called swing, where there's some acceleration, that is some movement and something you go down. and then eventually it ends with a heel strike. So you start with a heel strike and then you end with a heel strike. So this entire cycle of heel strike, then toe off, heel strike, toe off, heel strike, this alternating mid stance and other points of interest or features together comprise of the gait cycle. And what are we analyzing? We're basically analyzing these features. We are looking at, was there a heel strike in the person? Toe off tha ya nahi tha? What is the stride time? What is the time between two steps? How many steps did the user walk? When did stance phase stop and when did swing phase come out? These are very important parameters to understand how somebody walks. So if any of these parameters have a problem, then there is some issue with the gait. So that is the whole idea of understanding walking patterns in people using some systems. So traditionally, and there's one more interesting example, I'll quickly forward this also. So many of you must have watched Mission Impossible movies, all the parts. I don't know which part this particular movie is from, but if you see this, so basically this system here is a gait analysis system. Okay, it's completely made of cameras. Okay, so a person walks, these cameras are programmed to identify the person based on his walking pattern. He moves right down to his facial takes. Okay, you see this. Okay, there's a whole lot of software behind this. It's video based analysis. So it understands how your body's bones and muscles move, and that is very different. So it basically classifies you based on your gait. Kalyan walks like this. No one else can walk like Kalyan. No one else can walk like Dhaval sir, or no one else can walk like someone else. So if I try to imitate anyone, the algorithm will say, well, this is not your walking pattern because this is not how you put your foot on, this is not how you bend and walk and so on. Everything is captured. The system has learned your features. Your features do not match with someone else's features, so denied. So then somebody is trying to trespass. Okay, so if you can recall this movie Mission Impossible scene, you'll have a better understanding. So this is one other example of where gait analysis is done. Gait authentication. You can classify people based on their gait. Biometric we all know, face recognition we all know, but gait is also something. It tells a lot. It tells quite a bit of your body language, how you walk, and so on. So the major motivation for this project, this work that we have been doing, is actually came up by just observing old people. Okay, not very old, but people in your family. I'm sure there are just at least one person in your family who does not walk properly. Right? They could be bending and walking on one side, bending forward, or anything. It just doesn't matter. It could be 55-year-old person, 60-year-old, even younger than that. So basically this idea came to me just by observing my family members, my mother, my mother-in-law and others who are walking like this. So the question was, why are you walking like that? Well, they say we're growing old. Not very old. 60 is not very old, right? But then my mother eventually said, I started to feel some sort of pain. I slipped one time, I don't remember when. So from that day onwards, I started to feel pain on left leg. So I was not able to put more effort on the left leg. So I started to walk on the right leg. So then the walking, if at all, since it's a cycle, every time you put pressure on the left leg, you start to bend to the left and then walk straight, bend to the left and walk straight. So this just continued. They did not go and get it diagnosed. They did not know that they have to get it diagnosed. कुछ मालूम नहीं था उनको. वो they were thinking भाई ये तो हो गया मेरा, it's age, so there's nothing else we can do. So eventually it led to serious gait problem where you cannot go back. The doctor said it's too late. Okay, then age comes up, 67, 68, 70, then you develop bone issues, bones become weak, so on and so forth. But the previous 10 years, 60 to 70, this problem could have been diagnosed if there was some sort of an assessment systems. right? So age is one, accidents are one. Most common reasons: improper posture while sitting, while standing, while walking. Okay, if you sit now cross-legged, that could lead to walking issues. Okay, so if you're sitting cross-legged, please don't sit cross-legged. Okay, sit straight, no parallel legs. Okay, I learned this from my doctor when I had back pain, and of course medical reasons. So what are those medical or biological reasons? Sorry, from the body. Neurological causes are one. There are a huge number of reasons, neurology-based reasons why, which affect gait. Okay, one is stroke. They call it hemiplegic gait. Okay, the symptoms are swinging leg, flexed arm. I can share some videos later. Parkinson's disease. We know that disease has something to do with the brain, right? But the symptoms are you don't walk properly, reduced arm swing, and Alzheimer's. It's not here, but I read is there is something called freezing gait. People stop walking. Okay, the brain doesn't function, so they suddenly stop walking. Somebody has to trigger them and say, now walk again. Okay, so then there is peripheral neuropathy because of some issues that could lead to high steppage gait. You lift your leg and put it down. Cerebral disorders, because the brain is not functioning, the syncing is not happening, there's unsteady gait, you might walk fast, you might walk slow, so on. I hope I'm not boring you with medical things, but this is the basic foundation. And other sorts of gaits. Okay, there are also musculoskeletal causes, which is most common. We all know arthritis, which leads to antalgic gait, which is limping, shortened stance on the painful side. So your gait cycle is uniform on one leg, but it's not uniform on the other leg. There could be other congenital deformities, which we are not focusing on. There could be muscular dystrophies, and the kind of gait that comes up is waddling gait. You basically, you know, just keep moving back and forth. There's no steadiness, So these are all the different kinds of gaits, just a representative set: unsteady gait, high steppage gait, antalgic gait. These are all of these fall under the abnormal gait patterns. They're not normal. Normal means everything is in a cycle. There is no normality here, right? So the motivation was this. We started with a simple idea. Can I build a simple electronics device that can just capture somebody's walking? Walking is nothing but the pressure that you put. It's just started with that, and right now we are in this stage of trying to understand, categorizing different kinds of gaits. What was happening before is basically there was no assessments as such in every possible clinic. There was only camera based assessment, like we just saw in laboratory settings. You have an array of cameras, people would walk and then they would capture images or videos, and then image processing, video processing of frames, image by image would be done to analyze a lot of things. Very sophisticated algorithms, computationally intensive. You need to have CPUs, multi-core CPUs, or maybe even GPUs for that matter. The other was pressure mats. You have 10-meter pressure mats with pressure sensors. People could walk on those pressure sensors, and then how much pressure you put on the feet is captured by those array of sensors on the pressure mat. They would be sent to the data analytics part of the software. It would do all of these very detailed gait analysis and give. In India, these pressure mats or pressure sensing systems are only in few high-end hospitals. One is in Nimhans, one is in somewhere in Bangalore, MS Ramaya University of Medical Sciences something, and we also just got to know that CJ Hospital in Gandhinagar also has a system. It costs lakhs, 25 to 30 lakhs. I don't know what is the exact cost right now. So on the right, on the left, the table says different kinds of gait assessments. Okay, the most common, if you go to a physiotherapist, is just observe, right? So visual gait analysis, VGA. I forgot what R means. Sorry about that. But just look at you and say, okay, आपका left leg थोड़ा ये हो रहा है, ठीक है, we'll do some physiotherapy for that, and you go for 5-6 sessions, and then the physio will ask you, how do you feel? You would say, well, I'm good. Pain nahi hai mera, I'm ठीक हूँ मैं. So he would also observe you again and say, yeah, I think you're doing better than what you were last week or 10 days back. So that is all they do. Observation, and it's very easy, right? There is no data that comes for analysis or nothing. The other costly or expensive systems are motion capture labs, robotic, Moscow Skeletal Systems, IIT Gandhinagar has a huge research group on that, and so on. And slowly people have started to look at wearables. Okay, can we attach a smartphone to do this? Can we have a smart device to do that? Okay, and you need infrastructure for that. You need gate labs, force plates, pressure sensors, so on and so forth. Given this state of the art, given this, what is around there, what I came up with the idea is these will not work in an Indian developing country settings, as particularly in rural settings. I cannot possibly create a gate lab in a rural setting, create cameras and everything, and ask people to come and give me data. Neither can they come to my lab. So I need to have something that is mobile, portable, and of course the cheap or inexpensive part comes only when it becomes a product. But inexpensive here means how much does it take to create this device? Do I need thousands and thousands of rupees to have this? What is the minimal amount I need? I need a sensor, I need a microcontroller, that's it, and a few wires and some capacitors to start with, right? Breadboard level, and then go to the prototype. That is all we started. So what was the need for such a device is, like I said, majorly it is visual observation. So we have to come up with some data, and we are right on the digital era, right? Medical data is very important. So can we create a digital gate data repository, which is not there, and that is coming from the physiotherapy people. They don't have any data to analyze or learn. They learn from textbooks or some American database. We don't need American patients database. We need Indian patients database, right? So if I have that such kind of a data, I can give some quantitative feedback, whatever that feedback is, which can further help in assessing the effectiveness of a physiotherapy session. Okay? So that's the cost effective, and the next part comes in cost effective part of it. So these are the three sorry. Okay, so these were three major points, and that led us to come up with a device called gait tracker, okay, which basically has your MEMS accelerometer sensor cum gyroscope. It's a 6-axis degree of freedom device, and we basically started with ESP32. We are going to the next stage right now. So we just use this device and made up something. So I'll tell you how this accelerometer works. I actually created a GIF for this, but this PDF slide doesn't show. So basically your MEMS acceleration is a bunch of comb-like structures which will expand and contract based on amount of force that is applied. It is very simple. So if you move, it could expand. If you don't move, it could contract. Okay? And that expansion contraction gets converted into some kind of voltage values or some acceleration values, which is in G, 9.8 meters per second, 1G, 2G, 3G, and so on. And eventually the electronics converts it into voltage converts to G value, and you get it. So the analog to digital conversion, everything happens on that MEMS sensor, microelectronic mechanical system. So there's a miniature small ones. I'm sure many of you know these sensors, and they're already embedded on the smartphones. Without accelerometer, you cannot rotate your screen. Without gyroscope, you cannot play a game, racing game sort of a thing. So angular rotation, all of this is done by the gyroscope and your accelerometer sensor. They're already there. So we just looked at SDK, got that, started with a breadboard level version. Then we looked at slightly sophisticated version of that. And then we eventually looked at how do we design an enclosure for this. That enclosure took some time because we applied some design principles, product design principles of when somebody wears it around the leg as shown here, okay, or in the front side, there has to be some curvature to it, some ergonomic factor, so it is very easy to wear. So we designed this using a professional designer. Then we got it 3D printed so that it fits, the device fits inside. And these are the only components that we have in the device. You have the microcontroller, you have the MPO 650 sensor, which is accelerometer and gyroscope. And initially we tried pairing the device with a smartphone over Bluetooth, but Bluetooth connectivity majority of the times failed, so data transfer also failed. So we decided to use an SD card, an 8 or 16 GB SD card as part of the design. So it went through multiple versions of design, right? And it was battery powered, so lithium ion batteries were there. So we created this, designed this, developed it, tested it out across around 20 to 30 students who repeated data collection across an entire semester. Almost 70 to 80 data sets were given. We made sure that the device works. It gives us data. I'll show you what data it gives us. And then we started to understand what can we do with that, right? Parikshit, if you're there, if you can turn your mic on, you might want to add a few things so I can continue. Okay. Yeah, I'll move on. So what did we do is we collected this accelerometer data when somebody is walking, and then we wrote a simple algorithm to detect heel strike and toe off. That's all we did, right? So that is seen here. So heel strike and toe off. So every time I walk, my feet hits the ground, so that pressure is captured by the sensor, and then I toe off. Then when I'm toeing off, some acceleration is applied, so I'm moving, and then again heel off and so on. So then we detected the stance phase and the swing phase. That was a very initial preliminary level analysis. What did we do? The other analysis here was we wanted to understand whether somebody's gait can change. So like I mentioned, you're walking normally and suddenly you start to feel some pain and you think it's okay, maybe a painkiller se chala jayega, or apply some move or something like that. But so what happens during that time is you might change your walking. You might put more pressure on one leg or the other leg and start walking. Because of that, what happens, if you observe the first 30 to 40 days, your stride time is around 100 milliseconds, okay, per 2 steps or so on. And then suddenly your stride time starts to increase. Okay? So which means you're taking longer durations to walk because you're limping, you're feeling the pain, and so on. So what does that algorithm do is, its background, it is sort of monitoring, okay, these are all the stride times, pretty normal, ज़्यादा difference नहीं है. Now if you just look at the difference between two sample points on day 1, day 2, day 2, day 3 and so on, it's not a big difference, it's a small variation. But if you take, let's say, sample point at day 50 and sample point at day 51, and you calculate the difference or even moving variance, the variation is going to be huge, from 100 milliseconds to 200 milliseconds. So it's a big variation. Then it keeps going. So this trend tells us that the gait is changed. Some we don't know why it is changed because we're not medical people to make that conclusions, but it also at least tells us that something is being changed. So this is a warning signal to the user, because at that point we were thinking we will give this to the user to wear it. So the device would tell, look, आपका gait change हो रहा है, you might want to just go and consult a doctor. Yeah, Parishit, can you hear us? I mean, are your rights have been given, or should you be given mic rights? I'll ask Dhaval sir. My student Parikshit is also online. If you could just turn his mic on, he would be happy to speak.
Yes, sir.
Yes, sir. Yeah, so I'll continue, Parikshit. You can join once you are given those rights. So how does it? So yeah, I think this Parikshit will be the right person to talk about this. So let's just
Yes, sir.
pause.
Wait.
Yeah.
Sir Parikshit Joshi?
Yes.
Okay.
Hello, am I audible?
Yes, Parikshit.
Yes.
Yeah. Good evening, everyone. I'm Parikshit Joshi, a master's student here at Dhirubhai Ambani University. I'm performing my master's in information and communication technology, and I have been pretty much excited about the overall domain of how can we utilize the computing capabilities of uh, you let's say various kind of small scale microcontroller based devices, and we can utilize the capabilities of sensors to collect different kinds of data and how we can actually process them and extract meaningful information from it. So uh, first of all, I would, sir, can you go back maybe one or two slides, the slide showing the device? Uh, Sir, can you go back two or three slides maybe to show the device?
Yeah, yeah.
So I'll talk a little bit about uh, what kind of computation or what kind of components go into this device, and how we came up with the design, as well as how we came up with the idea of using these kind of small development kits, or say ready to uh, these kind of development kits in order to uh, sense or perform certain computations. So I would like to throw upon some light of the history of computation. Uh, let's say the computer revolution began from the 1950s and 60s. You had big computers the size of, let's say, rooms, mainframe computers, and those computers required lot of energy, lot of electricity to keep them working. Lot of infrastructure went into them just to keep them running and perform basic calculations. But now if we look that we have come up a long way, and we can certainly do a lot of calculations that those big systems were unable to do from our mobile phones, uh, or let's say with the progression of technology, with the progression of AI, GPUs have come into place, which has increased our computational capabilities exponentially. So uh, I'm going to talk about these development boards over here. So these development boards, the ESP32, which you can see over here, is somewhat different from let's say, your conventional mobile phone or your computer. This is a mini computer, sort of a say. It has limited computational capabilities, but it can perform lot of computational let's say uh, work specific computations at a very small scale. So this ESP32 here is like a mini computer in itself. It has a microcontroller. It has an inbuilt storage. It can perform certain type of computations. So when we were designing the device, we thought uh, we would require it to be smaller. So the form factor was definitely in consideration. So we were exploring different types of development boards, and then we come up with this. So this kind of board gives you a lot of computation powers at a very low cost, very low power device, and you can actually do a lot of things with the help of this device. So the next big player in our device is the MPU 6050 IMU sensor. So IMU is an inertial measurement unit sensor. So these kind of sensor, as Dr. Kalyan already explained, they have an internal complex structure inside them. So whenever, let's say, movement happens, then these comms rotate, or there's a fluctuation in this comms. That analog value is calculated, and then certain computations are done upon it, and a digital value is what we get. So these are extremely small sensors, and thanks to the power of computation and the progressing technology, they are available at a very cheaper cost. So since cost effectiveness is also a thing which we are targeting, these kind of sensors are extremely accurate and they provide results pertaining to our gate related analysis. So we have utilized the capabilities to collect the data of walking from these kind of sensors. So this MPU 6050 is a 6-axis sensor. It consists of two individual sensors. One is an accelerometer and one is a gyroscope. So the accelerometer is a 3-axis accelerometer. So it calculates the acceleration or the force in X, Y, and Z directions. And similarly is the gyroscope. It calculates the movement of your leg in, let's say, X, Y, and Z direction. So we utilize the capabilities of this IMU sensor and uh, extracted a lot of gate related features from the data coming from it. Uh, so there are let's say four main components of our device. First is the processing unit, which is our ESP32, which acts as the main processing unit for data collection as well as data pre-processing. Second is the MPU 6050 sensor, which is responsible for collecting data. Third is the SD card module. So since we are collecting gate data, there is a lot of data. We need to store it somewhere. So these kind of devices, let's say ESP32, they have a very limited computational capabilities. They are very specific, let's say in what purpose they are being used. So we had to find certain storage solutions. So for that, we have been utilizing the capabilities of 8 GB SD cards. So whatever data will be collected from the sensor, it will be processed by the ESP32 and the data will be stored on the SD card. Now to power this entire setup, we have been using lithium ion batteries. These are rechargeable lithium ion batteries. So as you can see in the casing over here, the device dimensions are 7 cross 7 centimeter. And one active part in this development is also to make this form factor even smaller. So we have been working upon that, how we can do that. Uh, I'll quickly explain you the functionalities of the device. It has two switches. One is for the power switch, so that will enable you to power the device on and off. And the second is the folder switch. So for example, if there are multiple patients and we want to segregate the data of each patient into, let's say, individual files, then the folder switch will help us in doing that. So this is the entire overview of our system. These components work together synchronously, helping us collect the data, process the data, and store the data, which will be used for further use. Moving on to the sample data format. Uh, so this is the sample data that our device collects. So here we can see 6 primary values. So these are 3 accelerometer values and 3 gyroscope values. Along with that, we are collecting the serial number of the datum along with the date, time, so that it is easier for us as well as the physiotherapist to uh, provide a quantitative analysis of the gate data. So we are utilizing the Wi-Fi as well as Bluetooth capabilities of the ESP32. So that microcontroller comes with a lot of other features. So we are trying to utilize the maximum capabilities of the microcontroller. So the Wi-Fi and Bluetooth are another set of capabilities which help us to track the real time of the data that we are collecting. So it is easier for us to map and perform further analysis. So here you can see accelerometer, 3 accelerometer values and 3 gyroscope values. So these are the actual values when you are walking. So accelerometer senses the acceleration of any component it is attached to. Your phones has a your phone everyone's phone has an accelerometer built in, a gyroscope built in, which performs different kind of functions. So we utilize the accelerometer data coming from the sensor in order to extract various gate related features. So I'll quickly talk about how we proceeded with the gate analysis. So there are two kinds of approach. So there are two methodologies. First is the data collection, and second is the data analysis. So for data collection, we have been using the ESP32, and for data analysis part, we have we have been utilizing various libraries of Python. Let's say NumPy, Pandas, SciPy, Matplotlib, to perform to extract meaningful features from the data that we are collecting. So from the accelerometer data alone, we are able to visualize these parameters. First is the gate cycle visualization. So gate cycle visualization is a plot which tells you or gives you an overview of your entire duration of gate cycle. So let's say when a device is attached, as shown in the previous figure, a device will be attached below your knee, and the patient will be asked to walk a certain distance, a fixed distance. So as in when the patient is walking, the data is being continuously generated. So that generated data is feeded into the system, and from that data, we are actually visualizing the gait cycles for that entire duration for which that person walked. Along with that, we are also visualizing the gait cycle duration for an individual cycle. So for example, in that particular session, the patient walked, let's say, 10 cycles. So for 10 cycles, how much is the exact gait cycle duration? Because if the gait cycle durations are uneven, then that signals that there is some gait related impairment present in the patient. Third, we are visualizing is a mean acceleration magnitude per cycle. So why acceleration is important? Because many of you might have observed that whenever we are keeping our foot down, or whenever we are going to perform a heel strike, then we keep the foot with certain acceleration. So let's say a person is suffering from pain, so a foot pain, then that patient will slightly keep the foot, let's say, with less pressure, so with less acceleration. So acceleration values help us determine if any kind of gait related impairment, specifically if the patient is suffering from a leg pain or other kind of gait related impairment is present. So that helps us a lot in identifying different gait related features. Also, we are visualizing the stance phase and swing phase as communicated by sir earlier. So a stance phase corresponds to about 60% of the gait cycle, and the swing phase is around 40% of the gait cycle. So stance phase is the phase in general when your foot is in contact with the ground, and the swing phase is the phase when your foot is swinging in the air. So if there is a difference in the duration of stance phase and swing phase, let's say a person is not swinging, let's say a person is keeping the foot on the ground for a very long time and the swing phase is negligible. So that also leads us to uh, certain kind of analysis that okay, these can be the features possible in certain type of gait. And last but not the least is the cadence. The cadence is basically the steps per minute. So for example, everyone has a different walking speed. Someone, for a normal person, the walking speed is around like 116 steps per minute. The cadence is around 116. But let's say a patient is suffering from gait related impairments, then they might walk slowly, or they might walk short step. So these are the different kind of parameters which we are extracting from the data which we are collecting from the sensor. Sir, can you show some plots?
Yeah, so I'll continue, and then you can come back. But thank you,
Sure,
Parikshit, for
sure.
that nice
Thank you.
description. So this is one data set that we collected, the one on the left, the raw sensor data of a healthy patient, one of the persons at the hospital who's actually a doctor himself, a PG level upcoming doctor. So we fixed the device like we showed earlier, and we asked him to walk around 10 meters, and fairly healthy adult. So if you see, there is a cycle, right? There is a very uniform cycle, but yeah, there are some points where he's put a little pressure, but otherwise, if we looked at the entire gait cycle, it's pretty uniform. There was no abrupt lifting of the leg or bending or anything. It was fairly normal. And so what did we do is we used a simple script in MATLAB that captures peaks, peak detection function. It will just detect the peak. And then we found out the distance between those peaks. And we said, well, these two peaks form one kind of a stride. So this is one stride versus another stride, and so on. So we then looked at in his entire, 8 minutes or 10 seconds or 20 seconds of data, how many such cycles are there? There could be 8 cycles, there could be 9 cycles. What is the time for each cycle? Is it 1 to 1.5? If it is, what is the, basically what is the value? Then what we did is we observed if there is a uniformity there, if there is a periodic pattern, right? So then we just looked at what is the stride time. It is 0.9 seconds, 1 second, 0.95, 0.8 point, and so on. And then we plotted the average gait cycle for that one gait session, or one walking session. Okay, that's the graph on the left, right, sorry. So the black is the mean average and the yellow spectrum is the standard deviation, like mean to max. What is the plus or minus? So for this person, for that gait session, for that one walking session, there were, let's say, 7 or 8 gait cycles, and the average gait cycle duration was close to 0.9 seconds. Okay, and plus or minus something. So it could go maximum to something, it could go minimum to something, and so amplitude also varies. So minimum it started from somewhere 7.5, the maximum could, but the pattern remained very similar. So this curve that you see was for that specific patient. Then I'm downloading a video of a patient that we collected data from, and I'll show that. Then this was another patient. So basically what we did was we also noted down the patient's medical conditions. So we collected data from 5 different patients. One was a 19-year-old female, a lady patient, a 42-year-old lady, a 58-year-old lady, a 56 male, a 58 male. Each of them had a different medical condition of their limbs, lower limbs. It could start from the hip to the lower limbs. So one was some kind of tibial fracture. We don't know the details. One had a muscle tightness. One had some arthritis on the left knee, something else on the right knee. Another person had a spondylitis, so on and so forth. So we just look, for example, patient one's data. Okay, it seems to have a pattern, right? From the left signal that you see, there are peaks, there are strides, number of stride cycles and so on, and the distance was the same. So same, if you see here, this is in seconds, but it's around close to 8 seconds, for example. uh, the same person, the same distance, this patient took close to 16 seconds to walk, so double the time. Okay, and Parikshit, you can talk about the one on the right where the stance and swing phase mix up. Yeah, so if you see the stance phase and the swing phase, the stance out of just that cycle I'm talking about, right? This is the average cycle we pick. The stance phase is around 0.6 seconds of the entire 1 second duration, and the swing phase was around the remaining time. So 60-40 fairly it was there. So this person already had some medical condition. The swing and stance phase had that proportional distribution of 60-40%. But the pattern is different. If you see this curve versus this curve, they're very different. Okay. Similarly, for another patient, if you see this completely different from the previous graph, there is no acceleration deceleration, which is showing you that you're moving from stance phase to swing phase. There's nothing like that. It could be that our algorithm has not detected it, but we are just working on that. So the pattern is very different, swing and swing phase. Similarly, for another patient, okay, so the pattern is very different. It's not just the pattern, it is the stride times. If you see, this is 1.4 seconds, this is 1.1 second, this is 1 second, so on. So then we summarize this average gait cycle durations for each of those 5 patients for one session. We are yet to analyze for multiple sessions. Each of them has given us multiple sessions of data, 5 days of data for patient 1, 7 days of data, 4 days of data, and so on and so forth. So we are trying to understand what is the consistency in the data. Is it 1.147 plus or minus something for the same patient for the remaining days, or is it increasing, is it decreasing, and so on. What is the benefit of this? The benefit is to assess the effectiveness of the physiotherapy. And if you go with the pain, you're not able to walk properly, your stride time is a bigger value. At the end of, let's say, 6 sessions, you should feel good. You should walk the way you walked before that session, right? Before your injury or something. So it could go down to 0.8 or 0.9. That is the whole idea. We are going to present analytics to the physiotherapist. Look, this patient's day 1 gait cycle was this much. Patient's day 2 gait cycle. So the gait cycle values are changing. What do you think? You think your physiotherapy is effective? Should you add more sessions? Should you add more things? So now we are making it completely data analytics based assessment from just observing. Okay, so that's the whole idea. And this one was not collected from the wearable device, but this was collected from the smartphone way back, which I showed earlier from one of our publications. So we collected data. We then did statistical analysis. This table here shows that. So using some existing research papers, we were able to come with some statistical analysis saying there are different kinds of intensity of gait abnormalities. Normal people have around this. Mild intensity could be around this, moderate, severe, and so on. Then what did we do? We just applied decision trees, naive Bayes algorithm to classify these 4 classes. Okay, so this is now getting into the machine learning part of it, where we have gait data. We're trying to classify different kinds of gait abnormalities. So what we found is, yes, decision trees do well because the majority of the data collected was from normal people. So, if you see that the confusion matrix there, majority of them are classified correctly. 30 people are correctly classified. There are some misclassifications between moderate and so on. So normal data gave us very good, almost 100%, almost close to that. In those days, we did not really find patients, so we tried to mimic, mimic matlab, try how somebody would limp. Thoda moderately limp kiya, severely limp kiya, mild, and so on. And then we did some classification. Of course, we took the help of physiotherapists to tell us how much is moderate, how much is mild. Okay, and similarly with naive Bayes algorithm also, we did some classifications. Then we repeated this on a 10-5-fold, 10-fold classification process, and we found some interesting accuracies. Okay, the dark one is decision tree and the light one is the Bayes. So around 89-90% of accuracy was there. It was just an attempt कि हमारे पास ये सेंसर डेटा है, इसका गेट एनालिसिस किया, गेट एनालिसिस से ये मिला हमको. Now can we categorize them using basic ML? Okay, so that is the another central part of this theme of this FDP is ML, right? TinyML or AI and stuff like that. So I've tried to cover this spectrum, right? Healthcare, societal impact work. So we are working on a healthcare device which has a lot of potential in the society, particularly primary healthcare centers, to collect data which is not there at all. That could really help in creating that repository or database of patients with different gait. I mean, there are databases, but not using such a device. People have done video-based capturing and so on, and that has a limitation, right? Like I said, I can't go to every place possible and install cameras. Neither can I install an array of smartphone sensors everywhere, because the computation requirement is also there. So how can you make everything simple is the goal, right? So I can take some questions. So before so the conclusions here is that we are in the wearable era, even in research, and a major absence in the product is something like this. There are some, but they're very expensive. Curop pod is one which we recently saw, but it doesn't do what I'm talking about. There is a smart ring, which is not very expensive, but that again does not do gait. So it is basically other healthcare. It helps you to do your basic mobility, sleep analysis, and so on. There's a huge scope in healthcare. We're actually now conducting proper, research, survey research to understand what is the trend in wearables in healthcare. Where are we? Where have we been 10 years back? What is the state of art right now? What is the current assessment levels in the market, especially in the hospitals and so on? The major challenge is not in the technical part of it. It's not the technology. Technology part is the easiest part. We have everything ready. We just have to create a nice SoC or mix and match these hardware pieces, try it out. That's the easiest part. The biggest challenge is user acceptance. So when we went to the physiotherapist clinic with this device, it was a big challenge to convince the patient to wear that, because it's something that you're trying to fit on his leg. They ask you all sorts of questions. ये क्या है? मुझे क्यों पहनना है? I'm feeling a bit heavy, ye thoda loose ho raha hai, and there is that hesitation to wear that because they think it's going to capture something unless we have to explain. But the same person might be willing to wear a watch, a smartwatch, right? So we are also understanding social aspects of that, challenges in wearable devices and acceptance of wearable devices, medical device. Is it going because one of the patient asked, "क्या result आएगा ये device से?" He said, "Instantly result नहीं आएगा." We are trying to analyze. So before I conclude, let me see if I can quickly download one such video of a patient that we recorded. Um, let's open, please. Yeah. Just observe his walking. His left leg and then the right leg. Right? So can anybody open your mic and say what you observed in the person's walking? Anyone?
Sir, wait, I will unmute the mic of participant, sir.
Yeah, sure. Go ahead. Yeah, yeah, we can open for questions.
Yes. Now, sir, participants can speak, sir.
Yeah, so anybody feel free to share what you observed in one such patient we just saw. Yes, Dr. Harnum Singh. Anybody? Whoever, I just saw some names on the screen. I can replay it again, just in case. Interestingly, this patient is also a doctor. I mean, you can be a simple observation.
Having some problem in left leg, sir.
Yeah, that's there. Left leg. It's a simple layman. Sorry.
I think there is a problem in stance phase, the initial, the mid swing and loading response. So I think the loading response when the person is having the weight on the, so that is the issue here.
Could be. Yeah. I'm just interested to get some observation point because I'm not a doctor myself. Yeah, it is one of this patient is a neurology patient. So from the slides that I showed, he could be having a high step edge gait. Your steps are so high, you lift your leg. I could be wrong, but your observation also fairly right? Is weight bearing is a problem, and then the loading response is taking a lot of time. So we are yet to analyze this person's data, this patient's data. So what we did is we actually plan to ask the doctor, what is it that you observe? Give us your observations, and we will try to connect it with the gait parameters, stance, swing phase, um, stride time. They might also be able to tell us, typically patients like these will have a very reduced stance phase or an increased stance phase. So we would use those clues or points and create customized algorithms for patients' medical diagnosis that we're doing, and then see what we can extract, because every patient has different things, right? So we can't have a generic code that can pull out the same thing. So it has to be customized. It must be programmed to understand the diagnosis and pull out certain features of that. So we are at that stage right now. There were other patients who did not have very obvious things like this, but they had problems. They had antalgic gait, they had wobbling gait. We cannot see that. We are not doctors, but they can observe. So now we are just trying to convert unka observations into data and present it in a better format, better visualization format. Okay. So that is about it from my side. There's a lot of scope in this area. We are just entering into this research area. Any questions, feel free, any suggestions, we'd be happy to take.
So, sir, are you going to feed the specific data to the to your system, like for a different stance and swing phase, whatever the abnormalities are there? So, are you going to feed particular data to the system, and then your system will compare the data, or then it will work?
No.
What exactly your system will work depending upon the different kind of patients?
No, so you're saying like, do we already know how much should the stance phase be, how much should the swing phase be for this patient, and are we going to use those values? No, I don't think there is anything like that. We are trying to understand from using this raw sensor data, what do we have to capture? Then the algorithm would be changed accordingly. So if the doctor says usually ऐसे patients में stance phase कम होता है, swing phase ज़्यादा होता है, because they may not give us these numbers. So then we would analyze, okay, in that case, will the heel strike be present? Will the toe off be present? And so on. We'll note down these symptoms, kind of. Then the algorithm will look for those important symptoms. Heel strike नहीं है तो क्या है? Toe off है, the next toe off कहाँ पे है? And then we'll do that. So there is no hard coded data that we will feed to the algorithm. Then it will pull out these things. It has to be dynamic. We are trying to understand those things actually. So that algorithm part is going to be very challenging also to tweak or modify it according to the gate abnormalities. It can't be one single abnormality, or the other way in terms of machine learning could be gather some features from these gate signals that we showed you. It could be time domain features or frequency domain, whatever it is. We can extract those features, feed it into the ML algorithms and see whether they can learn these features. Then we feed new set of data for maybe this patient or some other patient with different gait, and then can it do a clustering? Because we don't have any, if we don't want to do supervised, we could do supervised also, right? Now I know this patient has this medical condition, so it's condition A, this is the gate features for that. Another person has condition B, this gateway. So standard ML can be worked out. We can explore that. We can do that. Yeah.
Okay, so for any variations in the stance or swing phase, like generally 60% are having a stance phase and 40% of the gait cycle is swing phase. So if any patients are having any abnormalities in between the sub phases of stance, for example, loading response or mid stance, or even a terminal stance or pre-swing like a toe off when the toes push off the ground. So your system is going to just track the sub phases of the stance.
We want to do that, but before doing that, we have to understand how these features behave, or for that particular patient, ये patient में heel strike होगा या toe off होगा या stance phase loading response होगा या नहीं, उसके हिसाब से we have to understand, then we can attempt that on the code.
Yes. Okay, sir.
Yeah.
Thank you. Yeah.
Sure. Yeah. Thanks. Nice question. Yeah.
Yeah. Thank you, sir.
Any other question? Okay, sir. On behalf of all participants, I extend our profound gratitude to Dr. Kalyan sir for delivering an exceptional and enlightenment session. We greatly value the depth of your expertise, the rigor of your research, and clarity with which you articulate the complex concept, connecting them to real-world application. So, thank you, sir. It is a very good presentation.
Thank you, Dhaval ji. Thank you so much. Thanks all for staying late to listen. And yeah, we are open to any more suggestions offline also. If you want to try out our device at your nearby hospital, you can always get our contact and let us know. We have quite a few devices in the lab to share, to collect data. That will be really helpful if we can do that. So we can build a nice data set for further analysis. You could contribute on that also. Yeah. Thank you all.
Okay, thank you, sir. Thank you.